well, its properties, its physical nature, and the internal processes that are involved in fire. Why is it important to talk about fire? Because, well, it's a very common thing in nature and in human's life, but still it's a rather complicated process. So just the number of chemical reactions that are, well, going on when a candle is burning, it's amazing, and we can't develop a simple physical model to, well, predict the behavior of natural fires. So we want to understand more about it. Okay, from a point of view of scientists, fire is a process of rapid oxidation of some fuel. It's called combustion. Those reactions are usually exothermic. So energy is released through heat, through light, and also reaction products are also released, and we call them smoke sometimes. So we know also other oxidation processes that are, well, common in nature. For example, rusting and digestion, but they are much slower, so we don't see the, well, visual similarity with fire, but actually they have a very similar nature. Well, what conditions do we need to, well, obtain a fire? Those conditions are sometimes called fire tetrahedron. First, we need some fuel. It's some, well, flammable material that can be oxidized. Then we need some oxidizer, for example, oxygen. Then to start a reaction, we need a source of heat. So we need to get the material hot enough up some temperature that is called flammable point. And then to make the reaction go on, we need conditions for chain reaction. So, for example, that the heat would not diffuse in the area, but it would help the reaction to go on. So let's see it on just a simple example of a candle burning. What happens? The heat from the reaction melts the wax, and the wax rises up the wick, and it vaporizes. Once it's vaporized, it's very easy for its molecules to react with the oxygen in the air. Those reactions, they are exothermic, so more heat is released, and more wax is melted and vaporized, and so it goes on. We can stop it. For example, we could just take a candle and blow at it. And why does the reaction stop? Because we have taken, for some time, we are taking the heat that is released in this reaction just with airflow. So heat is released, but it doesn't help the reaction to support itself. So from our experience, we all know that, well, the process of burning, it involves emission of light and heat. There are two main sources of this emission. The first is the spectral band emission. It goes like this. The molecules of fuel, for example, just wax, they vaporize, they decompose, whereas combustion products are, well, produced. But also the flame energy, it makes molecules, vaporized molecules of fuel to ionize, and so they emit electromagnetic waves. So we can see it just as a visual light. The other source of this electromagnetic radiation is blackbody radiation of small soot that fly in the area of a flame. So what mechanism is more developed in this in certain kind of a flame? It depends on external conditions. So what external conditions can you think of? It's just like temperature, just because the intensity and spectrum of blackbody radiation depends strongly on temperature. Then it's oxygen supply, because if you have a very poor oxygen supply, then you will have a lot of soot produced in your flame, and then the concentration is high, so blackbody radiation dominates. Well, and fuel material, of course, also matters, because different materials have different, well, band spectrum. This is a device called Bunsen burner. just you can burn something and regulate the supply of oxygen. And at the left, maybe. Oh. At the left, you see a yellow flame that is with no premixed flame with no premixed oxygen. So we increase the supply of oxygen in the fuel, and at the right you see completely blue flame. How does this work? If we have no premixed oxygen, when we have a lot of soot particles, and they radiate, and the color of their radiation in visible light is determined just by the maximum of black body radiation spectrum. And if we increase the supply of oxygen, we first have less soot, and we have just more energy. With complete combustion is more energetic than incomplete, so we have more energy to ionize gas molecules, and so the flame becomes blue. Let's remember a bit about it. So this is a spectrum of black body radiation for different temperatures, and in the range of temperatures that we are interested in, its maximum is determined by Wiener's displacement law. So that's why if we take the most outer areas of a flame, they are red, and we go to the center, it becomes orange, yellow, and then what happens? Then the maximum shifts to the invisible parts of a spectrum, and so the flame that we see is actually blue. So we have talked about color of properties of radiation of a flame. But we want to also know about the flame propagation. So we can write the most simple model of a flame. Just we have a tube in which front of flame moves. So here on the right you have a yet unburned fuel. At the left the fuel is completely burned, and the all actual burning it takes place in a narrow region of width delta. We call it flame front. So as usually in diffusion processes, we can estimate the time scale of diffusion, heat diffusion, like this, where kappa is diffusivity and delta is this width. So another time scale is time scale of production of heat. It depends on the temperature. Is like activation process like. We want to obtain a stationary process of heat production and diffusion. So it means that those two timescales are equal. From this we obtain the estimation for velocity of fluid or velocity of front propagation. It's quite natural that if temperature is large, it propagates faster, and when temperature is low, it almost stops. Okay, and I want to conclude at this interesting experiment about the role of gravity in flame formation. Just because what we need to do if we want to learn about role of gravity, we want to eliminate the gravity. So the first man who do this was Paul Roney. He was dropping boxes with flames from a drop tower. And what he really saw, quite interesting, he saw that flame separated into small balls, very, very weakly burning. And they were floating around the box, avoiding each other and avoiding the walls also. So he could, for example, 2 seconds he could see those. He could take pictures. After this, he was doing it in space or something like this. This is also a picture of candle microgravity. Okay, I want to conclude that the process of burning is quite complicated. Natural fires can be well calculated, but if we study such a simple flame, we can predict, we can test our ideas about burning, because this it's the most ideal shape we can include in our model. Okay, thank you.
back to the last slide. So kind of touched on something. No, the last slide.
Last? Okay.
This one. So you said the left one was basically in something that was an job, microgravity job.
Yeah.
So you couldn't get that in normal gravity, or could you?
Well,
so maybe I'll continue my question, then you can answer. So when I was in high school, I made this experiment where I was creating hydrogen, and I gathered it in a transparent plastic bag. And so I had some hydrogen, and then I lighted it up, and kind of small fireballs of hydrogen started going up, and it looked nearly like this.
Really?
So
In normal gravity, were you?
Yes, in normal gravity. I never managed to repeat it, so the next time I tried it, it kind of blew up.
It was some gravity fluctuation. I don't know. Well, but I thought that if we have gravity, then the gas balls would obtain some non-symmetrical form. Well, I don't know. Maybe you can repeat it for us.
So I never managed to repeat it.
Yeah.
I didn't want to.
But the point in his experiment was that the elimination of gravity gives this effect. Well, I don't know.
It was just kind of curious.
Did you say it was hydrogen?
Yeah, it was so probably it's lighter, so it could.
Because hydrogen is really light.
Yeah.
So it was going up.
Maybe it's